Design, Build and Test unit is a team-based project where the students of the CDT 23 cohort work together as a team, applying principles of composite mechanics that they learn in the other units to design, build and test a composite structure prototype. The role of the client is played by one of the academics within the Bristol Composites Institute. This year was Professor Richard Trask and the NextCOMP team who set the challenge for the students to build a composite lattice structure that can be used as a conical shell in a rocket construction. They are supported in this by teaching assistants who are PhD students themselves, just further along their research journey. And this provides an environment of mentoring and peer-assisted learning that allows the students to gain confidence and expertise in composite mechanics.
So we were working with NextCOMP and High Power. So NextCOMP are a research group within the University of Bristol and Imperial, working on applying bio-inspired structures to improve the compressive strength of composite materials. And High Power are the University of Bristol's rocketry team. So they're currently in the process of developing a larger liquid-fueled rocket, and this became sort of the key design requirement and sort of the impetus for our project. So the aims of the project were to minimise mass and then try and improve the structural performance in terms of efficiency and resilience over conventional structures. So there's 12 of us working on this project. We've split into 3 teams, so there's 4 people per each specialism. At the beginning, we ranked our preference: design, build and test. For those with more engineering backgrounds, like myself, we've gone into the design, the FEA and the analysis. Those with chemistry and material science backgrounds gone into the manufacture and the testing to try and fit everyone's preferences and experience as well as we can.
So we're down in the clean room today. We are making the lattice design, which was inspired by the sea sponge concept. Sea sponges, found at the bottom of the ocean, managed to survive under massive pressures. So we took inspiration from that design and then hopefully trying to implement that into a rocket application. When considering the different manufacturing options, we could have gone with the traditional metal molds or a foam mold like this, and we decided to go for a foam mold mainly because we were able to produce much more of these as compared to one metal mold. This is SE70. It's a unidirectional carbon fiber. That means that all the fibers are aligned in one direction, and it's already infused with resin. We're choosing this actually because it's got quite a low curing temperature, and given the restrictions that we've got in our manufacturing capabilities, this really fit our design criteria. So after layup, we put a layer of release film over. After the release film was applied, we put a layer of breather to help the vacuum go through the vacuum bag. We then put that into a big envelope of a vacuum bag. The vacuum is then pulled, check that it's all nice and sealed. We then take that over to the oven, cure it at 70 degrees for 16 hours. Once that's cured, we let it cool down. We then debag it, cut the top and bottom bits of the component, then we pot it so that it's standardized for testing and rocket use.
So today we're doing some laser scanning with the ferro arm, looking at 3D scanning our samples. a lot of the time when manufacturing, it doesn't always go perfect. And the FEA analysis that we have currently are obviously very perfect in Abacus. So now we're trying to see what actually is the reality of this. With some of the baseline cones, because it's just ply, we have a lot of wrinkles that happen during the manufacturing. So with that laser scanning, we hope to pick up on the imperfections and the wrinkles, especially along the lines, and then feeding them back into the FEA, do the FEA compression testing with the new STL files that we get from the laser scanner. So now that we're pretty much finishing up the laser scanning, the next step will be the speckling of our specimens. This will be done with white paint and black spots on it. This is particularly important for the DIC measurements, and with it we're trying to measure the deformation and the strain of our samples during compression testing.
So the testing started this week on Monday, and on Monday the schedule was just to perform one test on the baseline design with the Shumatsu tabletop, that's right here, and we are using the 10 kilonewton load cell, and then we connected it with DIC to perform 2D digital image correlation. The test sample has a conical shape, and so the test rig has a bottom plate and a top plate to keep it in position. So the bottom plate is supposed to keep it fixed because that's the boundary condition for the application that is going to be used for. And the top plate looks like this, and that's to keep the top plate boundary condition pinned. Towards the end of this week, we are planning to do the rest of the test samples, which is to finish up with the baseline design and also with the lattice structure.
We just finished testing today. We had to test 5 cones so far, 3 baselines, 2 lattice with 10 kilonewton load cell. So for the baseline, it reached to 4 kilonewton, and for the lattice, it just went beyond that number or double, and that was around 10 kilonewton. What's gonna happen next is that we're gonna try to use the 25 kilonewton load on one of the lattice just to compare this with others, and then do the data analysis, and this is the end of the project.